left in class today. I don't anticipate it taking the whole time. Okay. So the first example I would like to do, I don't know. There we go. I just make it up actually. Is to find the angle between vector A, which is going to be 4i minus 3j, and vector B, which is going to be I plus 2j. So anybody who's done this already knows that to compute the angle between two vectors, I need to identify the magnitude of the two vectors, and I need to know their dot product. Because our angle between two vectors is cosine of the angles equal to the dot product divided by the product of the two magnitudes together, and then I have to cosine inverse to get the angle. So we're going to start with dot product. In order to find the dot product, it's usually easiest to put this back into vector form. So when we do that, vector A is going to be equal to 4, negative 3. Vector B is going to be equal to 1, 2. And then I would like to find a dot B. Here's where it's okay to use the dot because I'm talking about dot product, not normal multiplication. Anytime you see a dot, I'm talking specifically about dot product. We can only take the dot product of two vectors. We cannot take the dot product of a singular number being multiplied into a vector. That's something completely different. So taking the dot product, I multiply my like components together and then add their products. So the dot product of these two vectors would be 4 times 1 plus negative 3 times 2. I expect that my dot product is going to be a singular number, not another vector. So here I get my dot product is equal to negative 2. Did anybody get something different working through it? Okay, so I found the dot product of the two vectors. What else do I need to find in order to compute the angle between the two vectors? The magnitudes. I have to assume that each of these vectors starts at 0, 0 because I was only given 1 point. So that makes it really easy. We're going to start with the magnitude of A. How do I find the magnitude of a vector A? Square root and then distance formula. I know it's starting at 0, 0, so that's equivalent to my x component squared plus my y component squared. Adding them together and then taking the square root. 4 squared is 16, negative 3 squared is 9, gives me 25, which means the magnitude of A is 5. I will then go ahead and do the same thing with B. And when I do, I get the square root of 1 squared plus 2 squared, which equals the square root of 5. Any questions so far? So the magnitude is something we've been doing for a little while. That should not be new to us. The only new part was the dot product. And now we're just going to go ahead and put it all together, get back into this cosine equation. When I put it in there, I get cosine of theta is equal to my dot product negative 2 divided by the product of my two magnitudes. When I multiply 5 and square root of 5 together, I get 5 root 5. And I should have negative 2 over 5 root 5, which I can go ahead and put into my calculator. When you do, go ahead and give me the decimal to 4 decimal places. What decimal do we get for negative 2 divided by 5 root 5?
Negative 0.178.
Anybody else get that decimal? For negative 2 over 5 root 5. Okay, so then to find what my cosine is, I'm going to do cosine inverse of that number, and it's going to give me my angle. What mode do you think our calculator needs to be in order to find the angle between those two vectors? Degrees. It's actually okay if you did want to put it in radian mode, as long as you identified that angle as a radian angle. Obviously, we prefer not. We prefer that you do degrees. It's just a lot easier to compute and think about in your head. So I do prefer degrees, but if you wanted to do radians, I wouldn't say no. And then let's go ahead and round our angle to 1 decimal place. So what angle do we get? Say it loud and proud. 100.3 degrees. So that's how you find the angle between two vectors. Anybody have any major issues with that one? At all? Or did you finally? Okay, we'll look at it. Anybody have any other issues with this? Okay, let's go ahead and do another example. This one's going to be a little bit different. Orthogonality is just when your dot product equals 0. Parallel vectors have a cosine theta value of -1. That's just helpful information to know. So the next piece we're going to be doing is the component piece, and then that should actually go ahead and finish out our notes, because there's only a couple of that and work. Excuse me. So we're going to start with the component part of the notes. This example had 2 different questions kind of that we were answering. We're just going to answer one for the sake of this because they're both the same process. Okay. So this tells me that if vector C is equal to 10i plus 4j, and vector D is equal to 3i minus 2j, find the component of D on C. Hopefully you remember from the notes that we do actually have a formula that we use for component vectors. And this says that the component of D on C is going to be the dot product of the 2 vectors divided by the magnitude of whatever my vector is on. So this one is on C, so it's magnitude of C. And then we're going to graphically look at what this looks like and what part of the graph that this specifically is identifying for us. The good news is, since we have a formula, we're just going to follow the formula. So in order to solve this, I need to know what the dot product of D dot C is, and I have to know what the magnitude of C is. So we're going to start with the dot product. I would like to find D dot C. You have 2 choices from here. You can take each of these vectors and turn them into vector form with the little arrows on the sides, Or we can just take the dot product as is. The process will still be the same, and you will still get the same answer. So my dot product here is going to be the product of like components added together. So I'm going to do 10 times 3 plus 4 times -2. I'm going to find their products, and I'm going to add their products together. And when I do, I get a dot product of 22. And then I'm going to go ahead and find the magnitude of C because that's the other part of my equation. Again, C is just a vector that starts at 0, 0. So it is each of the components squared and added together and then taken under the square root. So the magnitude of C is going to be the square root of 10 squared plus 4 squared. Which is going to be the square root of 116. I go ahead and I put that in my calculator. Sorry, not this. And it's going to be 22 divided by the square root of 116. And I would like the decimal to the 10th place, please. No, let's go hundredths place. That seems better. So the component of D on C is approximately 2.04 units. We're going to put units on here because this is technically a length on a vector. So now that we've computed it algebraically, let's go ahead and look at it graphically so you can kind of see what this 2.04 represents on the graph. In order to do that, we're going to have to graph vectors D and C. So make sure I draw this big enough. Vector C was 10, 4. So I'm going to put a point approximately where 10, 4 is. And I'm going to draw a straight line going from the origin to that point. And then I have vector D, which is 3, -2. And again, I'm going to draw a straight line going from the origin to that point. And then we're going to look at the component and what that looks like on the graph. Okay, so the component, I actually kind of like to think of it as the shadow. It is the shadow created by taking a line perpendicular to my on vector and drawing it so it matches up with the end of my initial vector. So here, D was my initial, C was my on, because it's the component of D on C. So I want a line that goes perpendicular to C, but that matches up perfectly with the endpoint of vector D. My component then is the length of this shadow. I like to call it a shadow. It's the best way, in my opinion, to describe it. So it is essentially the length of the distance from the origin to that perpendicular point on whatever my on vector is. So here it's vector C. That is the length that is computed by this component. So it is the shadow on vector C created by a perpendicular line that matches up with vector D. I very rarely will ask you to graph it yourself. I might give you a graph and ask you to identify where a certain component lies, but I'm more likely to just ask you to compute it, because in my opinion, that's the more important part. Does that kind of make sense? So then if I had component of C on D, that would be a length that goes here. That would run perpendicular to vector D, but line up with the endpoint of vector C. It is possible for the component to be longer than the vector that it lies on. It's also possible for it to be shorter than the vector that it lies on. It could also be the exact same length as the vector that it lies on. It just depends on what other vectors I'm looking at. Okay, any questions on that? So the last little piece that we are looking at is work. I know, that's so much fun. I do have 3 examples in the notes. We're just going to go ahead and look at one of them because I think that would be sufficient. I'm going to pick the one I really want to do. We're going to go ahead and do technically the first, where I've identified it as the work kind of example. I'm going to go ahead and write it out, and then we will go ahead and work on it. Huh, I got it. We are. Oh wait, no, I don't want that. Okay. We are going to work on a work project though. Hopefully this is already in your notes, so you might not have to write it if you already have it written down. Okay, so this example says that the magnitude and direction of a constant force are given by A equals 2I plus 5J. That's really just a fancy way of saying that this is our vector. Find the work done if the point of application of the force moves from the origin to the point P for 1. So the first thing we're going to do is we're going to put this information on a graph because it's a lot easier, in my opinion, to go ahead and figure out what we're doing with it once it's on a graph. At least I think so. Okay. In the notes before this, I went ahead and wrote down approximately the equation that we were going to be using that worked for majority of these. And that is work is equal to the dot product of my two vectors. When we are computing work, we are usually computing work that has some sort of gravity component in here, which is represented by one of the vectors. So pretty much what I'm asking you to do is I'm asking you to compute the amount of work it would take to move an object from this point to this point with this amount of force acting on it, or the force of this vector acting on this movement. That's really kind of hard to imagine in your head. So we're really just looking for the dot product of the two vectors that are created by the force and by the movement. We know how to find dot product, right? That's not something new for us. We've been doing it now for what, an hour, close to an hour, and you guys did it on Friday, so it's not something that's completely foreign. So how would I find the dot product of A and B here? We just multiply like components, add their products together, and then that gives us our work. Do I expect for my work to be another vector or to be a scalar number or a singular number?
Singular number.
A singular number or a scalar. That's what fancy name for those numbers. If you get a vector, you have done something wrong. That is the number one mistake that I see happening here. Also, it doesn't make sense in the context of this problem. The amount of work should not be a point on a graph. It should be a number that exhibits the amount of work it would take to move something. Like if we say, I guess we don't really use numbers to describe the amount of work for us. Yeah, well, we don't use points either, so point still kind of works. If you get a vector, you are wrong. Anytime you do dot product and you get another vector, you have done something wrong. You probably just forgot to add your two products together. That is the number one mistake I see. So make sure somewhere in your notes or in your brain, you understand that dot product equals a singular value. It can be a huge number, but it's still just one number. So let's go ahead and do the dot product here. I'm going to go ahead and multiply my like components together. My issue here is that I have technically two vectors represented in two different ways. Does that change the way that I'm choosing to do my dot product? No, it's just that this one is in IJ form and this one is as a coordinate. Changes nothing. My first values are still my first components. My second values are still my second components. So when I multiply them together, I'm going to do 2 times 4 plus 5 times 1. 2 and 4 is 8. 5 and 1 is 5. 8 plus 5 is 13. I don't have any units here, so I really can't put a label on this work. Just know if we could, then we would. No, you don't have to find anything right now, but if we had like pounds per inch or something like that, that would be our work. Any questions on that? They look much worse than they actually are. Much worse. Okay, so the rest of class, I don't think it's as much time as I wanted. Oh, there's some time, like 20 minutes. It's homework time. It's a great time for you to ask me questions if you have any over any of the problems that I gave you in the homework. Or if you have the homework done, it's a great time to just help your peers or do something else. Yes. Yes, I'm actually contemplating not even